Let's get started. So, hello everybody. Welcome back after to the first colloquium after the vacation, or at least for most of us, probably after the vacation. So we're very happy that today's speaker is Dr. Jeroen Linssen from Strukton Hogeschool. So let me quickly introduce Jeroen. He's working as an associate lecturer in applied data science within the Ambient Intelligence Research Group. And today's talk is also going to be about something related to that, I guess. And is titled Applying Data-Driven Techniques to Analyze Industrial Use Cases. So yeah, we're pretty much looking forward to today's talk. And if Jeroen is ready, then you can share a screen and take us away.
Definitely. Thanks, Tom and everybody for having me and for giving me the opportunity to give a little bit of insight into what we've been doing at ambient intelligence as a whole, but also specifically related to some use cases that also feature things related to PrimaVera. So indeed, as you explained, my title is Applying Data-Driven Techniques to Analyze Industrial Use Cases. With the slight subtitle, in theory, it works in practice. So what I actually want to do in my talk is to kind of give you an overview of some of our experiences in applied research, which is a term to kind of distinguish the research we do at universities of applied sciences from the academic research. But I also very much want to highlight and emphasize a few things concerning that and how I feel, at least, that we can maybe improve collaboration with each other and also with companies. I think beforehand, if you have any questions or if anything is unclear about things I'm talking about, just wait a minute or two to see if I'm still explaining them or will be explaining them, and otherwise just raise your hand and ask a question. That's fine by me. So who am I? Yeah, as Tom already said, I'm an associate lecturer. I have a background in mostly AI and a bit of the human-computer interaction side of that as well. So also the human factors involved in designing technology, developing technology to do something intelligently by itself, so autonomously. And I kind of phrase it within our research at Ambient Intelligence as AI to measure and model man or women and machine. And most of our research is kind of domain agnostic, but I have kind of two main domains that I'm working in, so predictive maintenance, industry, and also healthcare. Just for you who are not completely aware of ambient intelligence, it's a research group at the Strukton, and all of our research kind of revolves around these three main research lines. So along the kind of typical scientific act paradigm. So on the one hand, we have connected embedded systems, so sensing information, getting data out of environments, out of people, out of systems, then doing something with that data in our applied data science research line, and that's the one I'm responsible for. So that mostly revolves around more advanced statistics in the end, or AI or machine learning, whatever you want to call it. And if you gain some information out of that, you also obviously want to communicate that information to end users or other types of users. And that's where our augmented interaction line comes to the front. And it mostly revolves around more technological aspects of giving feedback about the information you gain from your data analysis. And to the right, for your convenience, buzzword bingo to capture all the cool words and terms that are flying around nowadays. So you can cross all them off because we all do all of them. So that's for ambient intelligence. I'd like to kind of start off with a few take-home messages. You might call them propositions. So I just also noticed that Tom is doing his PhD research. Propositions are the most important part of your PhD, Tom, so pay attention. No, just kidding. I think these are just two messages that kind of relate to our experiences, our lessons that we kind of learned. They might be kind of given or kind of superfluous, perhaps, but I think they are still important to emphasize. So the first one is to actually use some kind of process methodology if you're when you're doing research. And I will highlight that one specifically related to data-driven analyses, and it's called CRISP-DM. So more on that later. And the second one is that for practical usage, usability is more important than the latest state-of-the-art technology. I think that's kind of a dangerous one maybe to utter here in front of, well, all the researchy kind of people, because we're all doing like kind of the newest and latest and greatest technology that we want to evolve or evaluate. So this is kind of a knuppel in het hoenderhok, but I think it's also important to highlight this, especially in context of deploying solutions in the real world at companies, etc. So that's also what I want to cover during this talk. And it also very much relates to our take on applied research. Okay, and it would be nice also to kind of give a short history of something that we were doing related to our applied research and how we see data analytics, also data acquisition concerning IoT and sensor solutions. And it's actually a project that we finished a few years ago, which was called Data and Smart Industry. And it was almost as broad as saying that, there are some companies and they want to do something with data. I think that's a very, very open kind of question, not necessarily sure if it's even a research question, but we had two goals in the end. So on the one hand, we wanted to give SMEs, so the midden-kleinbedrijf, the means to take the first steps on the road of smart industry. So, and the second one was to develop some kind of generic and easy to use system with which SMEs can then both acquire and also analyze data. And I guess in research it's also very much a given that any proposal you write has to be ambitious to get funded in the end, but also to do something interesting, it also needs to step beyond the state of the art. So I think these are two goals that we are still working on, and not necessarily goals we fully achieved during this project. And there are a few reasons for that, and to a certain extent, there are very, very practical reasons as well. So just to give you a picture of a few of the companies that collaborated with us, Saxion and also at the University of Twente, in this project, you see the companies, and just glancing through them, you can already recognize, okay, a few of these use cases have the same kind of goal in mind. Companies vary a little bit. They are all kind of manufacturing use cases. But there it was also very tricky to kind of find the common denominator. Obviously you want to analyze some kind of data, but your domain, your context matters a lot. And I think that's also kind of a given, obviously. But it also made it tricky to, at least for the second goal, make some kind of system that is generic enough to cover all these use cases, to acquire data and analyze data. So that's also something we obviously found out that was too challenging to realize for all these companies. So what we tried in the end was to, at least for each of these use cases, at first build some kind of prototype or some kind of approach to help them at least make some steps towards smart industry. And this is kind of where one of my take-home messages also comes into play, because I think you can make the distinction between exploratory and kind of deployed research. And I think on the one hand, so one example use case there was a collaboration with Nijhuis Industries, and they make kind of cleaning solutions for cooling systems. So they have some kind of chemical reaction that they can do to clean cooling water to combat Legionella, for example. And they definitely have some data there, or at least we thought they had some data. Well, they definitely had data, but the quality of the data was not necessarily that high to make very, very good estimations of the effectiveness of their redox reactions that they implemented. So on the one hand, we were happy that they already collected some data, and we were able to just showcase some very basic machine learning algorithms to further analyze, okay, what the effect of these redox reactions was for certain systems. But like in the end, the complete solution wasn't necessarily satisfactory because, as I just said, the data quality wasn't that high, so it was hard to extrapolate and to make predictions for future processing of the whole system. So that was kind of a tricky one there. It was kind of exploratory to find out what was possible with machine learning and the data that was already there. And I'll come back on the topic of data quality a bit later on. But on the other hand, so this was on data analytics. On the other hand, on data acquisition part of things, we also had a group of students who were actually very, very eager to actually build something and implement it. And we were actually very proud of that result. This was at Penthouse Molding. So it's a company in Almelo which uses rotational molding techniques to kind of make plastic containers, varying in size from a small jerry can to a 6,000 liter kind of rain dispenser. And what they actually did was they made a sensor solution to measure whether the silos containing the resource material, so the coarse granulates that get molten into a mold, to determine how filled they are. So either they're completely filled, halfway filled, or almost empty. And this was to give better insight to the company, okay, which silos do we need to replace at a certain time, because it takes a little while. You need to take them out of production and then fill them quickly and then put them back in there. And they actually went as far as developing, or at least connecting, these relatively simple sensors to a very nice PCB of their own design, which they got printed. And they didn't just implement it on one of these silos. No, they implemented it on a whole row of these silos. And I think the company there was also very much, to a certain extent, actually amazed that they got this far. So they also got hired over the summer to roll this out over the complete factory, so to do it for all the 40 silos that are there. And I think here you see, okay, you might ask yourself, okay, what is the actual research part there? I think the research part here is that they managed to at least set up this whole system. So they actually design it. So that's kind of deploying everything and implementing everything, but also validating that in such a setting that it actually works and works in a stable way, so that the company can actually use them in production. So that was a very, very nice result, I think, that actually came out of this this research or this project. So we experimented a little bit with some use cases there, and still we wanted to kind of tackle everything and bring everything together to see whether we can still make some kind of generic methodology for all the companies, so to at least help them further along when the project ends, for example. So we try to still cluster these use cases related to data acquisition and data analysis. And in the end, we made kind of a whole kind of slightly some kind of a maturity model for everything that we want that you want to achieve using data. And just a few questions that I point out here. So what is our business goal? What data do we need? What are the data sources there? And how do we analyze our data? And these are very, very typical questions. And this is also how we got around to a process methodology that I just mentioned, CRISDM. I will explain that in a few slides, because that also helped the companies better understand how they can structure their projects related to data. But first, to also kind of make the kind of level the playing field between us as a University of Applied Sciences and the companies, we kind of had to think about, okay, of course, everybody wants to do new and cool stuff and use AI or whatever. But okay, how does it relate to your whole process? What do you actually want to achieve with this? And what we got around to was that, people many times have this kind of intuition that, sure, there is some data, there should be some data somewhere, I guess. We want to do some kind of analysis, maybe using AI, because that is very nice and cool. And then we get to some kind of insight. So that seems kind of straightforward. So the immediate counter question we always ask companies is, yeah, sure, what is your actual question? What comes before the data? Because it's nice that you have maybe some spreadsheets or a few databases lying around somewhere, but what is your question? What is your business goal in the end? So that's, I think, very important there. And based on a question, you can actually at least investigate which kind of data is useful to answer that question and which kind of analyses you have to do to get a proper insight. And it's not necessarily that this this happens just in a linear fashion, but also that yeah, you have some kind of insight, and it might turn out that you don't have enough data, or your data is of low quality, as I just mentioned. So what do you do then? Yeah, obviously you want to acquire more data. Maybe you want to develop some kind of sensor solution indeed to acquire data out of the environment or out of the systems. And then you go around this loop again, and you think a little bit about the analysis more, what kind of techniques are actually applicable to this new kind of data. And in that way, you kind of run around this loop. I think, in a nutshell, this is kind of what is captured by CRISPDM, which stands short for Cross-Industry Standard Process for Data Mining. And I guess quite a few of you might already know about it, but I'm just going to explain it in a few words here, also to kind of structure the use case I want to talk about, because it's very much an iterative model, as you already saw. Yeah, you need to iterate over your findings. It's not a matter of having one data set, doing some analyses on that, and presto, you're done. No, you really have to go through these 6 stages. In any case, if you want to also properly integrate it with your whole yeah, business process. And it's actually a very, very yeah, nice and very structured model, and it's extremely yeah, structured in such a way that it's very hierarchical in a sense. So you're just a very brief schematic overview of that. You have these different phases, there are tasks in that, and there are lots of steps that you can take in that. And it's available through this link at the bottom if you want to know more about it. So to kind of emphasize that, just to put these 6 phases like this in a neat row. Every phase has, for example, certain kind of sub-phases or tasks, so determining business objectives, assessing the situation, etc. And these each have their own sub-tasks as well. So it's very nice to work with, and at least you can build a very structured kind of approach to your data-related problem, and it also helps companies to actually figure out, okay, where are we needed? How can we align our things? What is necessary from our people, from our end as well? So that also very much improves collaboration in our experience. So I want to show you a use case where we took this approach right from the start, and we deliberated that with the people at Scania from the start. And this is a project that has been running for a few years already, and it's together with Scania production in Zwolle. Just a few facts there. There are about 2,000 employees there. They produce about 180 trucks per day, and it's a bit more than 60% of the whole of Scania production in Zwolle in Europe in total. And they're very much lean on-demand production. So as you can see in the picture here, the trucks queue up nicely. And none of these trucks is the same as the one before it, because they're all very much on demand and customer specific. What you also actually see here is that they don't drive right at that moment, but they are carried by these carriers. So these are kind of somewhat autonomously driving carriers that obviously carry the trucks through the whole factory floor. So that's 1 kilometer of line, during which all these trucks never stop moving. So people have to walk along with them to montage everything on top of them. And at the end of the whole line, after a kilometer, you can simply start the engine and drive off with the truck. So it's extremely nice to see and also to visit. So they actually, I hope they currently already, again, organize tours again, because that's what they've been doing in the past as well. It's very impressive to see how efficient and optimized it all is. But obviously, what we started with Scania was also defining what their actual business goal is. So what they wanted from us, or how can we help their processes. And the main thing actually there was that they wanted to reduce downtime. So you can imagine, here in a queue, if one of the cars stops or one of the carriers doesn't go any further, then there's a definite kind of queue and a kind of traffic jam in a sense. And that costs, calculating it back, it costs about 500 euros a minute. So every minute counts, and they would definitely want to reduce these occurrences. So translating that, they want to really figure out what are the possible causes of unplanned, so corrective maintenance on these carriers, because they want to definitely prevent that. And in the end, they want to move towards predictive maintenance, so that they can actually say that, okay, let's plan a maintenance for this carrier in a week or two, because it's not been behaving very badly, but we expect it to do worse over time. So let's stay in front of the actual downtime that it might cause. So it's kind of very basically phase one. It also incorporates kind of assessing the whole situation. So this is kind of a somewhat laborious process, but it really works well to map all the things you have to do. So whether those are resources concerning personnel, data warehousing, certain requirements, constraints on what is available and not available. So for example, documentation, we actually had to go through some kind of physical documentation stored way back in the factory somewhere hidden to get a feeling of all the carriers that were in place there. But also whether they have enough people available for us to talk at, and at which moments we can actually discuss findings that we might have. But also, for example, several risks that might be there. So we might not have access to all the sources, or maybe some data sources are not relatable to each other because of different registration procedures. So all these kinds of things you kind of map in this first phase, and then you start translating, okay, what are then the actual data mining goals? So that's like a step after that. And we actually had two there. So one was finding correlations and notifications. So kind of the notifications that pop up in their dashboard. Let's say, okay, for example, this carrier is running a bit slow. There's a stop there somewhere, things like that. And in the end, we also wanted to find possible causations for a very specific alarm for the carriers. And this specific alarm was already something that might be something serious based on insights from the domain experts that were walking around there. So that's also something we set out to investigate. And then in the end, we make a project plan. Okay, we plan according to CRISP-DM. And it's very nice because it very much incorporates iterations and the risks and contingencies. And there's obviously implicit agile development with this type of plan. So it also aligns well with software engineering practices, as we will see a bit later on. So based on this whole project plan, we went to a phase of data understanding. So we actually needed to collect the data. So what we got in the end was, quite a nice collection of, tabular data, so columnar data, which we sought to describe, explore, and verify the quality of those. And I will just spell out a few of these things that we also had to do to really get a good understanding of everything, because it's been kind of censored for the purpose of presentation. But we had a lot of different attributes relating to the notifications. So that was all database of a bit more than a year of notifications of their whole production line. And what we then set out to do was, okay, let's check a look. Let's see what we can get out of this data. So what is actually the meaning of these variables? Because some had somewhat cryptic names. Some columns appear to have some redundant information, so that was also interesting. And there were also definitely some data quality issues. For example, 90% of the values in some columns was missing. That was also, as it turned out later, due to changes in registering notifications from a certain point on. But all these things we immediately or quite quickly found out. For that, we had to actually return kind of to the business understanding phase to refine the data mining goals, whether they were still attainable with this kind of data. And in the end, yeah, we already figured out, okay, some of these might not be attainable, but still we went or we pressed forward. So, and this is kind of, yeah, what you typically see in data analytics. So obviously we want to discard redundant information to make the data set as efficient as possible. We want to impute some missing values where we could, transform values to make it a bit more easily usable. Also made use of this very nice pandas profiling, which already gives a nice overview of all the things that might be wrong with your kind of data set, or at least it says something about your data quality. So this is kind of our standard procedure of taking up these kind of assignments. And then starts kind of finally one of the fun parts, because data exploration to us, most often means some kind of data visualization. And it's nice to work with lots of fancy colors and types of visualization, as long as they kind of provide some good information, obviously, about the data. And you might start indeed quite naively with some kind of correlation matrix. I'll kind of skip over that because it's kind of self-explanatory. So the higher things correlate with each other, or the lower, the stronger the correlation is. And there might be some kind of factor there that relates these two kind of features. Also, we registered, or we took a look at the distributions of, for example, the duration of certain notifications, when they started, when they were solved. So, for example, how long a certain stop or downtime took at a certain station or with a certain carrier. And also very nice, and it's my classic example of what you can get out of data exploration. This is kind of a mapping of all the instantiations of notifications over the whole time span of the data set. And it's very nice because you can get lots of nice insights out of this data. So for example, there's a whole nice bar of white here, which means as much as, yeah, there were no notifications at that point. And that's usable information, because then you can determine, oh yeah, that was a summer vacation, so they were out of production for 3 weeks, as they do every year. So obviously there are no notifications. But jokes aside, you can also see some interesting tidbits here and there. So for example, in the top row, you see a few co-occurrences of notifications of a specific type, only on one day or very near to each other. So that would already be some kind of, a highlight of that. Okay, this kind of notification only happens once in a while, and it's very much a unique kind of appearance. And some you might see are way more occur way more often, but it's only a visual interpretation at first, obviously, as you can see here, but it already helps to kind of check what you can focus on from the start. More different visualizations, anything you can think of. So a heat map of where in the factory, in the actual line of a kilometer long, certain notifications arose, and also cumulative times of notifications per station, so per station in the line. So all this already helped us a little bit to figure out, okay, what can we zoom in on and what can we actually get out of this? And we did a few very basic, at first, statistical analyses. And I'll just skip to the kind of lessons learned there, because, yeah, it's more of a lessons learned and confirmed, because a few of these things were already very much known to the people walking around at Scania. So, for example, yeah, we know that certain locations correlate with notifications. Okay, that's what we can prove, using our data exploration and our analyses as well. Certain notifications are main time consumers, also very clear. But also we couldn't find direct causal links for urgent notifications. And that was based on a variety of analyses we attempted to do, but also the data wasn't very rich in certain regards. And that led us to believe that, okay, there is a necessity of lower level data there, because these are only the notifications about, okay, something is happening somewhere and somewhere else there's something different happening, but we don't have a proper insight into the actual functioning of the whole factory line. And I think there we learned a valuable lesson there as well, and also Scania, that, okay, we need more data out of these lower level systems. And I'll come to that in a moment, because another thing was, okay, never mistrust the gut feeling of a domain expert. I think that's also wise to mention, because in the end, what kind of the domain expert already predicted turned out at the end of the year to also be confirmed by us that indeed that's exactly how it is. So yeah, it's a good exercise to go through all the steps, but indeed, yeah, what he said was also right. Included kind of a given or typical kind of phrasing here, garbage in, garbage out. Yeah, the data wasn't very rich indeed, so we couldn't get much out of it. I think that's a typical thing you see nowadays. But the current steps obviously are collecting this lower level system data and to design some kind of IoT and sensor solution to acquire data. And we're actually working towards that, and we have implemented one solution before the summer vacation, which is very, very basic and looks like this. So it's a kind of shielded box with a Raspberry Pi just to register temperature, voltages, and a bit of the functioning of the carrier in which this is located. And also there you see some kind of hurdles to be taken there. So for example, it's nice that you can collect the data on a Raspberry Pi, so on some kind of storage device or SD card even. But how do we get this information into some kind of data set? So our initial idea was to use Wi-Fi, but also there it's tricky to use Wi-Fi in an industrial situation because of limitations at the factory floor. So that also it's still an ongoing endeavor to figure out how we can best do that. So more on that soonish, I hope. But this is at least a step we took there to acquire more data and to take a step actually, or to make that this whole iteration of designing a next solution for gathering more data and then doing more analyses based on that. So that's what we'll be doing, or what we are doing currently with a continuation of this project together with Scania. And this is just one example of what we've been doing as very much applied research. So it kind of feels like, okay, you're exploring data, you're doing data analysis, you want to get more out of it. And it's all, maybe it might feel kind of basic in that sense, but it's also because of the application towards a specific use case. We also have a second example, which is quite a bit more data rich, and also somewhat related, obviously, to PrimaVera, and it's on point cloud segmentation together with Strukton Rail. And it's basically summarized as, we want to investigate how we can automatically recognize objects in the railway infrastructure of the Netherlands. As you can see on the right here is a picture of a typical, of the catenary system, so the bovenleiding in Dutch, and all the constructions around it, so the beams, the cross beams, anchors, and all the typical objects you have in that kind of construction. And you might ask yourself, okay, sure, let's do this. And I already mentioned in the title here, point clouds, and that's what we also used as a basic data set to try to recognize and identify objects within a piece of railway infrastructure there. So this is kind of the whole pipeline that we have in mind. So based on some kind of point cloud, we do some pre-processing to actually make it manageable to identify objects. Then we segment objects within that point cloud, and then we convert these findings into CAD drawings. I think two things to mention. First one off is point clouds are volumetric 3D data, so they are mostly captured by LiDAR systems. So you have some kind of 3D information about your environment. So I'll go over that in the next slide. But the second one is that, okay, what is actually the case with Strukton Rail? Why do they want to do this? So using the whole 6-phase setup, the the first phase is obviously business understanding, and what they obviously have is that manual inspection of these kinds of infrastructure that is already in place is laborious and can be dangerous because you're standing close there. There might be trains just running around still. So you want to automate that as much as possible and prevent as much manual inspection as possible. And secondly, there was also a desire to improve the design process. So this is based on current infrastructure, but also what kind of information can we get out of the current infrastructure to improve the whole design of the new infrastructure. And in the end, obviously, it's like which objects are where in the railway infrastructure. And you might think, okay, sure, they already have drawings of everything and a database of everything where everything should be. That's partially the case, I think, and it's not specified in a level that you know exactly with all the specific coordinates where everything is. So the second phase of PrimaVera is data understanding, and we want to figure out how we can segment point clouds and identify these segments. So these are kind of the data mining goals there. And as might be apparent to some of you, LiDAR datasets are quite large. So we got a few of 15 gigabytes of data per dataset, of which there were 4, and that's for 1 kilometer of track. And in total, the Dutch railway has about 3,000 kilometers, so that's kind of a lot of data. And you can also see that indeed, one part of this 1 kilometer was already 800 million points of data, and a single catenary arch, so the bovenleiding you just saw, is already 3 million points. And it's tricky in any case for computation. But a second point in which it was tricky was that the density of these point clouds was kind of inconsistent, and it's something you can see on the right here. So these are the data set is captured by some static LiDAR apparatus, and you can see that indeed very close to this apparatus, the density is quite high. So you see lots and lots of points, but the farther you get away from it, the lower the resolution, so to say. So that was also very tricky, especially when you want to figure out, okay, where certain kind of small objects in this data set are located. I will also touch upon that in a minute. Because what you can see here is just an example of this whole data set. And I think the first thing to do is just to kind of go about it naively. So that's what we did. So we want to figure out, okay, where are these beams and cross beams located? So where are these actual catenary arches, as they are called? Now, we did some relatively straightforward computer vision processing, just a basic thing laid out here. And in the end, we were quite comfortable with just locating the actual catenary arches from the data set. So taking a slice out of that and then using that as our data set based on which we can actually determine where certain objects are. So that already saves us a lot of computation in the end. So that's kind of the data preparation before we can start modeling. And for modeling, we actually dove into the state of the art. So the best things we found that were most applicable to these kind of data were 2 approaches. At first, PointNet, which was also developed, so a deep learning approach to, in any case, figure out whether you can segment parts of a certain object, but also do semantic segmentation. So, for example, in this data set, can you recognize chairs in the environment, walls, etc., etc. And there have been a few iterations on PointNet already, and it was very nice. But what we also saw that in the validation studies of PointNet is that most of the objects that are being segmented or recognized, that they are of the same size. And as we figured out through experimentation with our data set of the railway system, is that, we don't have this kind of similarity in size because I think a large degree of order of magnitude of variance in size of objects that we have is about 1 to 20, 30 or something, because we also wanted to recognize quite small insulators versus the large beams and cross beams. And that's kind of why we also brought in a superpoint graph, which is a very nice approach, which also made a lot of sense to me intuitively, at least, because it focuses on some kind of hierarchical structure of points. So for example, in the picture here is, which might be apparent to you as well, is some kind of table plus chair, I would say. And what superpoint graph as an algorithm does is it tries to relate certain groups of points, so superpoints, to each other. So there's some kind of contextual information there, and that made a lot of sense to me. So for example, also in the railway infrastructure, you wouldn't very often see the railway tracks above the cross beams, for example, or any such kind of hilarious examples. So we also try to evaluate that, and these are the two approaches we selected in the end. And well, yeah, these were the results, which is nice because you have some bright colors. But what does it actually mean? It means that every color there is also some kind of segmented objects. And at the top, you see the results of the point net, and at the bottom, you see the results of a superpoint graph. And what we actually discovered is that, yeah, superpoint graph doesn't work that well on everything, but it works quite all right on the smaller objects indeed. But we also want to obviously validate this numerically. So just a little bit of background there. We use the mean intersection over union to determine how good a certain algorithm performed on our data set. And it's basically simply the overlap of the classified object versus the object that should be there as ground truth. So the higher that overlap is, the higher the score, obviously. And scores were quite all right for this data set, at least. I think the state of the art on other data sets is about 0.9, but this one is, as I just explained, way more varying in sizes of objects. So this was also already a very good result, and we're still working on getting this even farther with some ensemble methods to do proper data analyses. But I think it was also important to mention here that indeed you need to consider the evaluation of this approach and to actually make it comparable, so to actually explicate how good your model performs in the end. And then comes deployment as a kind of a final phase in CRISP-DM. And that's a lesson we kind of really learned relatively recently. What's very important there is to get the software infrastructure in place. And this very, very much relates to my second take-home message. So it's nice if you build lots of cool models, but if you don't integrate these and implement these in the processes that are already there, they will not get used. So that's kind of basic thing. So what's actually necessary for that is a very proper alignment with the things they have already running as Strukton Rail. So that's what we're working on now. So to develop, in any case, some kind of API that they can easily call and which can give them the information they actually need to build a kind of CAD drawing based on these point clouds in the end. And this is somewhere, the merger between software engineering and data science very much, to get this whole data management pipeline up and running, you also need to think about, okay, how can we deploy these things? And that kind of brings me to our current and future challenges, both in this project, also with Scania, but also for us as a research group as a whole. And I think that especially goes for our kind of applied research, because we want to, in the end, evaluate it in situ, so on location as much as possible. And that means integration of everything. So deploying it to some kind of, maybe not production environment, but at least some kind of test environment at the companies. Software-wise, it makes sense to do some very good dependency and environment management using Docker, obviously, but also validating the data management pipeline. So is it stable? Is it robust? Can we actually trust it in the end? And then in the end, our main goal also as a research group is also to work towards automation. So to actually build into our research more the kind of data ops way of thinking. So as I just explained, data science plus software engineering, it's a very short shorthand for data ops, but it's way more than that because you need to consider data engineering, security, quality, and integration to actually make it happen and make it work there. So I think that's a very large challenge in any case, also for us, but also for companies to make this happen. And I think, my personal opinion there is that there is too little attention for that in the end, actually. So that's something that might also be for PrimaVera, something very interesting to discuss how we go about this. One thing I also want to mention is that, okay, it's nice if you have these kinds of data pipelines running and they are automated to a certain extent. Okay, but also coming from the human factor side of things, how do we make people, let people make use of these kind of systems, and how can we make sure that they actually trust it, and how can we make the models that are implemented, how can we make them insightful? So I think a very prominent research avenue there is also like kind of explainable, or as I would like to term it, interpretable AI, at least, so that you can see, okay, why was a certain decision made by this model? So I think that's also very important to focus on, especially also if you want to implement it in the end. And third challenge, and I think that goes for all of you as well, is aligning with education. Because we see the links with software engineering, data analytics, and multidisciplinary projects. But okay, how do we make it so that the research we want to do, the projects we have, the use cases we have, how can we make these work for students as well? Because as we can all agree on, these are very, very challenging subjects that we want to tackle. So how do we properly design assignments for students in the end, and how do we also make sure that we teach them the right things to do, so to prepare them for the work field in a few years. It's not something I have an answer to, but I think it's something to keep on thinking about, at least. And finally, I have some kind of an open question, maybe to you all, or maybe something to discuss about a little bit within the context of PrimaVera, how we also go about collaborating along the whole design and development of techniques, technologies, and systems that we want to implement in the end. So how do we go from an academic level to a production level? I think it's still also very tricky for me, but also, I'm not sure what everybody's opinion about this is. But I think it's tricky to scale quickly, at least, from a low TRL to a high TRL. I think that's also a given. But it's also, I think, a challenge we face within the PrimaVera project, because we do lots of cool stuff, but we also want to take it to a quite high TRL in the end, because I think that's what the industrial partners are also asking for, obviously, in the end. So that's something maybe to discuss also within PrimaVera, maybe now, maybe at an upcoming meeting as well. And I'd like to close off with a few reiterations on lessons learned that I mentioned. As I said, they are kind of given, but that's why they are nice lessons to just keep on teaching. And I think the first one is, in any case, align your process methodologies. And I mean aligning as in aligning your process with all the stakeholders within the project you're doing. So in any case, with your industrial partner, with your researchers, with your educational partners, your students, your teachers, etc., etc. And at least for us, for our research at the Ambient Intelligence, it helped a lot to use the standard methodology of CRISP-DM. It's not necessarily perfect or entirely complete, but it makes for a very, very nice framework to, in any case, also synchronize all your activities that you want to do, and to also make people aware that you're working on these steps, and that they don't have the kind of wrongful assumption that you just model something based on some data and that's it. No, the other steps take way more time than simply modeling it in the end. And I think also, it's kind of, it's should be mentioned in the same breath as aligning with process methodologies. Explain what you do, so justify why you are doing, certain steps in your process. And actually, there's a slight commercial break there. Just recently, I, together with a colleague of mine, I gave a nice training session on AI methodologies, data mining, machine learning, and deep learning in 3 parts. and that's freely available. So we also send that out to companies with which we collaborate to at least also make them aware of maybe the basics and also the slightly more advanced things of AI and machine learning that are out there. So it's also nice. You can also access it freely. So feel free to check that out as well. And then finally, to get back to my one of my take-home messages, don't focus too long on fancy models, but get the infrastructure up and running for deployment, because then you can actually evaluate things in practice. And I think that's something that's very often overlooked. And with that, I want to thank you for your attention. And if you want anything more, or maybe you had enough, but maybe you want more, then you can simply send an email or just visit our website. That's also a given. And I think the final given for now. And if there are any questions, I would gladly receive them, but maybe Tom has some.
Yes, thanks a lot, Jeroen. Thanks for the very nice presentation. I think it was very nice to hear your experience from these past projects. So indeed, if anyone has any question, you can either you can just unmute yourself and speak up. But in the meantime, maybe I was also wondering about one thing. Maybe I missed it somewhere, but in this last use case, so the goal was to build these cut drawings from the LiDAR data, right? But when you then have these drawings, what was actually in this case the kind of goal? What to do with these drawings? Was that something specific, or?
Well, yeah, in any case, to get a proper overview of all the infrastructure that is in place right now, so with the correct objects, but also to help in the redesign of certain stretches of railway track. So, for example, obviously there's lots of maintenance on the railway tracks, but if they already have the cut drawings of existing situations, they can more easily edit them in the end. So I think that's the main thing there, and that will save them a lot of work.
Yeah, I was just wondering if there was even something maintenance related there, in the sense that you can even detect things, but that may be too much to ask from these point clouds.
It's something we definitely mentioned indeed. Yeah. We run similar projects on bridges, so that you can also capture a few point clouds to see whether they sag, for example. Well-known example in this consortium, I think. And I also mentioned this to Strukton Rail, and it's something that might turn out into a parallel line of research together with ProRail, I imagine.
Yeah, cool. All right. Yes, I see a hand raised by Marielle.
Sure, let me switch on my camera.
Hey, Marielle.
Yeah, hi. Jeroen, thanks for the presentation. I enjoyed it. I have one remark, maybe. It's on the relation, on the marriage between data science and software engineering. I mean, I like this a lot. I advocate this often as a computer scientist. I advocate it a lot. Usually I say, well, data, you have a car, and data is the fuel, and computer software engineering is the motor. You can also switch it, but at the same time, in PrimaVera, we chose not to focus on software engineering, basically because the program is already very wide, very broad, and with people with different backgrounds, different expertises, different companies. So that is why, even though this topic is close to my heart, it's not in this project. And I also like your educational module, so maybe we will follow up on this.
Good. Thanks. I think it's a good remark indeed. You can only do so much within a already large project.
Yeah.
But it's good to be aware of, okay, there things are possible with software engineering, for sure, that should be done in the end.
Actually, this is something I advocate. I am in the Dutch AI coalition, also on behalf of Saxion, and there I advocate this a lot, that software engineering is an integral part of data science, and
Yeah, we do our best to put it on the agenda. That's clear also from our side.
Yes.
All right. Let's see. Is there anyone else who has a question, maybe?
I do have a final remark, because we have planned the consortium meeting of PrimaVera on the 25th of November. You have received an invite, and we're still figuring out how to exactly organize this. It's nice to do it live, but physical, but yeah, and this whole Corona business is taking longer and longer, so we're figuring out what the best way to go is there.
Yeah, it's good to know.
Yeah. Okay. If there are no other questions, then I would like to thank Jeroen again for the very nice presentation. And then
Thanks, my pleasure.
I wish everyone still a very nice afternoon, and see you all next time.
Yeah, thanks. I'll see you soon.
Yeah, bye-bye.
Thank
Bye.
you. See you next time.